Hello everyone. Let me just share my screen real quickly. All right, hello. Okay. So I hope everyone can see this. See? Right, sorry. Sorry about that. I didn't realize I probably need to open this in Chrome. Google sometimes a little bit difficult. See. Sorry about that. Let's see. All right. Okay, so maybe if things stop working or you stop hearing me or something weird happens, please let me know, because I don't have overview over the presentation or what it looks like. But yeah, as you mentioned, I'm from Merantix. This is I'm going to tell you about the data retrieval challenges facing autonomous vehicle developers today. So I've recorded 10,000 hours of driving data. Now, what is a typical question that these days it might be asking themselves? A little bit about Merantix. Maybe I don't need to explain it too much. You might know it, and Nicholas already mentioned it. But it is a venture studio, which means that it doesn't build products. It builds companies, and we already have 3 companies. Merantix Healthcare, that does automated breast cancer screening, Amex Labs, that mostly focuses on machine learning and AI for consultancy, and then Merantix Automotive, of which I'm a part of, when we are developing SEA Search platform that I will be telling you about today. So a short introduction and an overview of the problem and how you want to solve it. And as you might all know, the amount of data that autonomous vehicles create today is exploding. Up to 10 terabytes of data could be produced by an autonomous vehicle, which, just to put it in context, is around, I think it's around it's like 100 smartphones worth of storage data. That's per hour that the vehicle produces, which is quite a lot. And with all this data, it's very difficult to actually find the useful data in there that you need. Find that, on top of it being really difficult to find it's quite expensive to make sense of the data, because you have just a bunch of raw data. You need some manual labor to label the data, tell you what's in there. Maybe someone watches a video after you recorded the data and puts in, here's a lane change, here someone cut us off, or oftentimes there is a person sitting in the vehicle while it's driving that has an iPad that kind of marks things in. This obviously doesn't scale when the amount of data increases. And on top of that, infrastructure costs of storing this data is explode quite rapidly, and I will discuss that in more detail later. And the fact that most of this labeling of the data, or kind of making sense of the data, is done manually, means that you can only ever use a minority of your data, because there is only so much data that can be looked through. That means that majority of the data actually remains unused. And this is kind of like a high-level idea. I will go in much further detail of how this works, but this is kind of our solution to this problem. So on the left, you can see the raw data. It's the data, represents the data from the vehicle. You feed it through some data processing pipeline, and this data processing pipeline kind of adds a layer of data on top of the raw data that kind of explains what's actually happening in the data. So this could be, is there a pedestrian in the scene? Is is a car? Is there a lane change happening? Or something like that. And this additional layer of data is then fed to a database that can be accessed through a user interface or some sort of a programmatic API. Wait, just let me real quick make sure. So is everything is working? Yeah, okay. All right. Okay. So yeah, I just was a little bit paranoid it wasn't working, but it looks pretty good. So let's continue. Okay, what is all this data about? What kind of data is this? And what is autonomous driving about? So, this is kind of a very brief introduction. I kind of expect most of the people who attend these things to kind of know this. But there's a large potential in autonomous driving, as you might all know, low cost, more universal mobility, increased road safety by removing people from the equation and unlocking productive commuting. This is kind of summarized in this, my favorite stock photo of this unreasonably handsome man reading a book, very relaxed on a car that's just driving him somewhere. And yeah, so not everyone knows this, but autonomous driving is not a binary thing. It's not like either a human is driving or it's fully autonomous. There are multiple levels of automation. Level 0 being, no automation. There's just a person driving. Level 1 is could be typical brake assistance or cruise control in your car. Level 2 or 3 are kind of hard to define, but you can kind of think of the current state of the Tesla autopilot. Level 4, which no one has reached yet, is high automation. That would be a car that drives you around, maybe in a city or on a highway or both. But then when it comes to a gravel road, it says, okay, I cannot handle this, please take over. So it could be like kind of a conditional, fully automated vehicle. Level 5 is basically a car that doesn't have a steering wheel and can drive you wherever you need it to take you. This is what a typical vehicle that AV developers might use. So this is a Toyota research vehicle, and I mainly want to draw your attention to all the sensors on top. There's the cameras and the lidars. There's like a bunch of them. This is just to give an idea of what all this looks like. And the main, different companies have different setup, but the heart of the setups are usually these 5 sensors. So it's the camera, lidar, GPS, radar, and IMU. And camera, I guess we all know, it just, camera that record videos. This is a relatively modest setup with 6 cameras. You can see in front, the back, left and right, all around the car. So it can get a 360-degree view of its surrounding. Then you have a lidar that, in very simple terms, shoots out light beams from the car all around the car and builds a three-dimensional representation of the surrounding. So it basically allows the vehicle to tell, okay, where is the closest car, where are the pedestrians in the scene, where are the trees, etc. So it gives an idea of what the surroundings look like. GPS, I guess we all know and love from our of cell phones and many other places, just where you're located on the map. And on top of that, we also have radar, which often serves a similar purpose to the lidar, but has different strengths and weaknesses. And then the IMU, which in simplified terms just allows the car to figure out how it's moving through space. So this is kind of the typical setup. And all these sensors, they produce a lot of data. And just to put this in context, here are kind of like back of the envelope calculations of storing data for a single car. So let's say you have one car, you are developing an autonomous vehicle, you have a single car, you drive it around for 1 year, around 3 hours per day, about 300 days per year. And then you want to take all this data and you want to store it for another year. And the cost I'm using here is just typical AWS Glacier storage or cold line storage from Google. So here, like the calculation, it will produce around like 30 terabytes per day, which means it's like 10 petabytes per year, which in turns into $500,000 per year just to store data for a single vehicle. And this is only the cloud storage part. This is not like, the logistics, all the hard drive that you need, moving the data around, nothing like that. It's just cost of keeping it in the cloud. So obviously it is impossible to store all the collected data. And even if, in theory, if you could store all the data, only a limited part of it is interesting. But, and you would like to find this interesting part. On top of that, what is kind of interesting, like even if you can store all the data, and these companies, they usually have a lot of data, but 95% of the data is not really accessible because you don't have any labels or any idea what's in it. So if a company needs to, let's say they're training some vision algorithm and they want to improve pedestrian detection, add junctions, because junctions are by nature really hard. They, instead of looking through the data that they already have, record it, because those scenarios are definitely in there. It's easier for them to just send out 10 cars and tell them, okay, go around, find intersections and record scenarios where there's a lot of pedestrians. So this is kind of one of the main things we want to solve, is to be able to unlock the power of this data that you haven't accessed yet, instead of always recording something new. I spoke about these interesting scenarios that you want to keep. They really depend on who you ask, but here are like some examples. As I mentioned before, crowded junction are interesting. There's a lot of traffic signs, traffic lights, moving participants. Often there are a lot of pedestrians, so that's of course interesting. If there are construction sites in the way, that's very important. If agents in the scene, and by agents I mean just kind of actors, vehicles, pedestrians, bicyclists, etc., if they behave unexpectedly, that's something you would want to keep to be able to evaluate your systems in. What is this data used for? The most obvious thing, obviously, is to train some machine learning algorithm. You have a neural network that you want to do, path planning. How do you drive on a road? Then you need some data, and you need to curate the data in a specific way. Or if you have a vision algorithm that you want to train, that could also be a use case. Often it's used to evaluate systems. So maybe if car manufacturers are developing a brake system, they need data that allows them to see if it's working accordingly. And then, it could also be, you want to figure something out about how cars drive differently in Berlin versus Hamburg, and you want to do some data exploration and just answer some questions. These kind of things these kind of tool would also help you do that. All right, so let me just also real quick, everything looks good. So what is our solution? I already gave a high-level idea of it, but I'm just going to reiterate it for cementing it further. This is a bit of a different view. Like I said, on the left, you have all the sensors that I mentioned before. You feed them then through some processing that adds a layer on top of what's actually in the data. And then here under automated tagging, you can see we've classified the data into like how important it is. So, crowded junctions are very important. Left turns, it's relevant, but maybe you don't need that many left turns. And then you have, low value data like empty highways. There's only a very limited subset of data about empty highways because it doesn't contain a lot of information. This data is then stored into the databases I mentioned before, and then it can be accessed in different ways. These metrics, we develop a lot of metrics, and this is kind of a list of a few of them. Maybe you want to know something about how fast the car is going, something basic. You want to know as a developer of autonomous vehicles, if you're doing some overtaking maneuvers on a highway, maybe you need to develop an automatic honker that honks every time someone cuts you off. Then you would need to know what if there are cut-ins happening. Then there's some other things like location, visibility of the scene, weather, and many, many more. So this is just like a short list of things you might be interested in as a developer of these vehicles. So this is kind of the overview of autonomous driving, and what we are kind of proposing is some sort of a framework that allows you to retain the correct data and search for it easily, such that you find the correct data. So these are not screenshots from the product. I was a bit too afraid of doing a live demo, so just have a kind of a slideshow mock-up of it. But let's say now I am developing autonomous vehicles, and I'm interested in finding a scenario where there's a yield traffic sign, there's a multi-lane urban environment, and there's a right turn and a lane change. Like what might that actually look like? And I search for this, and I might get something like this. Just one question: does the GIF work? Could you maybe the moving picture? Is it moving for you guys? All right, cool. Just wanted to be sure. I've had some problems. I've had some problems before, but great. All right, sorry about that. So I looked for these three things, and this is what I got. It is indeed, there's a yield sign. It's in the city, and it's doing a right turn and a lane change. But even though I only searched for these three things, there are much more information in this short clip. There's, for example, the lighting conditions. There are shadows outside, and it's pretty bright. The weather is sunny, and there's a construction site. And this data is all something you will pull in when you get this clip. And there are many, many more different things that you can get from a clip like this. Another example, I want to find pedestrians crossing the street, very low maximum speed, 30 kilometers per hour in, Karlsruhe. What might that look like if I search for it? I might get something like this. And as you can see, this is like a very challenging scene. There are a lot of pedestrians around. There's a lot of hard things to navigate. And, if you're developing an autonomous vehicle, this is definitely something you would want to keep. This is like an important piece of data that has a lot of information that you need to evaluate your systems on. So on top of this, like I said before, you get, even though I only asked for these three things, I get much more data. There's a driving goal is mainly collision avoidance. The category of your road is pedestrian area, and the environment dynamics, which is basically how much is happening, is very high. So now I kind of want to get a little bit more technical and dive into how give a kind of high level overview of how we developed a lane change detector, which is one of the extractors and one of the metrics we are interested in. And just so everyone is on the same page, this is what a lane change looks like. We have a car, it's in one lane, then it moves and it goes to the other lane. This is actually kind of an interesting scenario, just as a side note, because someone is cutting you off, and therefore we change lanes. And why do you want to find lane changes? Well, first of all, as I mentioned before, it costs a lot of, why do you want to find, let me rephrase, why do you want to find lane changes automatically? First of all, manual labor is expensive. You don't want to have a person sift through a bunch of videos or sit in a car marking these things. That doesn't scale, and it's very expensive. And secondly, lane changes are inherently interesting because they are, in relative terms, they're quite a complex maneuver. You have to know a lot about the environment. Is the other lane empty? What's happening around you? And so on and so forth. And in this case, they're often correlated with other interesting events. So this is something you would want or might want to find in an automated fashion. So first approach might be something simple. let's use a trajectory. Let's see if when our trajectory is curved, and when it's curved, we know there is a lane change happening. So what do I mean by trajectories? Is basically the data we get from the IMU or the GPS of kind of how the car drives through space. This is like attractive because it's very conceptually simple, but these kind of simple approaches often break down because they have a lot of corner cases. And of course, this is a very simplified example, but this is kind of more to highlight and illustrate the point of, everything has a corner case, and the simplest approach doesn't always work out. So in this case, I've kind of highlighted a simple corner case. The trajectory of moving from one lane to another is exactly the same as driving on a curved road, and driving just along the road. And there is like actually no way of knowing which is which or disambiguating the two. So as I said, simple example, but this didn't really work out for us. So then the second approach is just to bring out the big guns. Let's just go for the neural networks and train like an end-to-end lane change detector. You feed in a sequence of images. The neural network learns from the data to find, when is there a lane change happening, and everyone is happy. That is, that works well, and it is the state of the art. I think in most machine learning problems and neural network solutions are, especially computer vision, are the state of the art. And if you can get them to work, and if you can get over all the engineering hurdles, definitely the way to go. But I kind of wanted to use this talk to kind of emphasize and illustrate the problems that you have to, or the questions you have to ask yourself before you decide to go with a neural network. So here I've listed a few of them, and I kind of want to talk about them in succession. So first of all, as probably everyone knows who's tried to train a neural network, they're tricky to train. It's hard to get them to work generally. And people often speak about the 5 stages of training a neural network that I'm very familiar with. It's denial, anger, bargaining, depression, and then finally acceptance. This is also known well known from psychology. And just, for context, on the right, you can see these training curves that you spend a lot of time looking at when you train neural networks. And in this example, of course, there's no context, but here, these lines, first of all, are not supposed to be squiggly, and they're quite squiggly. They're all supposed to be kind of the same, which they're definitely not, and they're all supposed to go down. So these are the kind of things and challenges you face when training neural networks, and they can be, quite difficult. But all joking aside, the things that you run into are, hyperparameter tuning, all the knobs you have to tune, what learning rate do you choose, how large should the image be, what kind of data augmentation do you do, which requires a lot of work and a lot of engineering. The bugs you get with neural networks are actually really infuriating, and I bet a lot of you have some war stories from there. Often, at least these large computer vision models have like long iteration cycles, so it might take, from multiple hours to days to train it. So if you want to try something out, it might take you 1 day to train it and figure out if something worked or didn't work. So that really slows the development process down. They might learn the wrong thing. It's kind of the classic example of, if all lane changes happen around, I don't know, it's a simplified example, but like the Brandenburg Gate, then it might just learn that if it sees a Brandenburg Gate, there's a lane change. And they can be quite tricky to evaluate. Additionally, they are very data hungry, and they need a lot of labeled data. And it can be, quite expensive and time consuming and difficult to actually find labeled data. So, this image just is kind of, first of all, to kind of illustrate the point that labeling data is time consuming. So the red boxes are a prediction from an object detector, and the green boxes are the ground truth labels that are annotated by a human. And as you can see, of course, it's a different problem, but it's object detection. But as you can see, that this is it requires a lot of work and a lot of time to label this data. And even though neural networks are quite good, one of our main challenges is that all the data sets and all the data we get are different. So there are different camera setups for different manufacturers. There are different aspect ratios. You have different parts of the world, and often these things can have a substantial effect on the generalization. So like something that works in, I don't know, Karlsruhe might not work as well in Berlin, or if you change the aspect ratio or something. This is a bit of a cherry-picked example, but this object detector was trained on the image below, and then it was evaluated on the image above. And as you can see, to reiterate, the red boxes are the predictions for the object detector. It does work very well on the image below, but on the image above, where it has to generalize to a different environment, it's not very great. So this is one of the challenges we face, because all manufacturers have different data. So we have to make sure that everything we develop is very generalizable. Then, of course, as I mentioned before, we are feeding a lot of data through our pipelines. So neural networks can be quite slow. So we have to be absolutely sure that it doesn't slow down the processing, and that it's fast enough that we can process the data, the amounts of data that we actually want to process. So yeah, to reiterate, if you can use neural networks, you should do it, but there are a lot of engineering consideration and things you have to think about before you kind of take the plunge, because they're really hard to get to work, and they're really hard to maintaining from an engineering perspective. Okay, I kind of took a deep dive into a few cons of neural network. So just to reiterate, we are developing a lane change detector because lane changes are inherently interesting. Our second approach was a neural network, but we decided it's too much overhead, it's too difficult to get to work. So what is the third approach? Well, the third approach it looks something like this on a high level. You take your raw data, you crop a part of the data so that you can see kind of the center of the road in front of the car. And why do you want to see the center of the road? Well, you want to see the lane markings, because the lane markings tell you if you're making a lane change or moving from one side to another. Then you detect the lines, which should correspond to the lane changes. And because lane changes happen in time, we need some sort of a time component. So in the end, we have a Markov model that kind of chains together predictions over time to tell you if you're doing a lane change, in this case, from right to left. This is quite relatively simple model. It does require some training data, but not a lot. However, detecting the lines didn't work that great. So we actually added a step of having a neural network in there. And this is exactly the same. And the only thing changed is that we took this image, we feed it through a neural network, and the neural network tells us, is there a lane in there or is there not? And the reason why we added this is because the line detector was very noisy. So it detected a lot of lines where there weren't supposed to be lines. And therefore we have kind of a neural net to make it less noisy and make it more robust. And now you might be asking yourself, okay, didn't he just spend 10 minutes before talking about the difficulties of using a neural network? That is true, but this neural network, has some. We could put it in there because, first of all, it works on these small image patches, which means that it's quite small because the task is not very difficult, so it's very fast to run. Secondly, because we crop the image, we have reduced the kind of generalization. So like a crop of a road in front of a vehicle is going to look relatively the same no matter where you are in the world. So the generalization is not as problematic as before. It does need labels, but it doesn't need as many labels as a task of predicting a lane change from a full sequence of images. So it has some drawbacks, but because it improves the performance a lot and it is quite small and easy to manage, we put it in there. Then we have this kind of approach that finds lane changes this way. So to kind of summarize it, this model is, I didn't mention before, but of course, neural networks are not very easy to interpret. So if something goes wrong, it's kind of hard to tell why it went wrong, but this model is quite interpretable. This model needs labels, but it needs much fewer labels than the kind of the full neural network solution. It's modular, which means that you can, like, these individual components can be kind of switched out. So we can change the line detector, or we can, maybe I remove the Markov model and add as LSTM. That's no problem. I could do that if I want to. And last but not least, and one of the most important factors for us, because we process so much data, is that it's like very fast. So this is kind of, okay, let me go here. So now we've developed this lane change detector, and this is how it fits into the whole framework. You have the raw data on the left, you feed it into a data processing pipeline, and now you add the information about is there a lane change happening or not on top of the data. You store this lane change information in the database, and then the users can query it and ask, okay, I want to find lane changes. Please give me all clips that include lane changes, and they might be able to get that. Just as a small caveat, this is kind of a simplified overview of the lane change detector. It has a lot of room for improvement. There are some things in there, but in the interest of time, I won't discuss that here. But if you're interested, you can ask in the questions and answers. So that's it for me now, and I guess we can move on to questions and answers.